Hello, my name is Ryan Matthews. This is my final project for ME 344. My project is on ceramics in microelectromechanical systems. As a bit of background on microelectromechanical systems, otherwise known as MEMS, they're microscale devices commonly used as sensors, dispensers, displays, or communication devices. The primary feature of them is that they work in the microscale, but generates effects on the macro scale. Two examples below are the single axis accelerometer. Accelerometers are found in phones and other devices. They measure the acceleration of a device. Additionally, because they do react mechanically to changes in voltage, they work as inkjet printer nozzles as well, where the membrane pushes out ink through the chamber and through the feed-through. Most MEMS use silicon as their material because they can use the same technology they use to make semiconductors, which is photolithography, to make them. However, silicon is not a very strong material. It's not good structurally. And so for certain applications, such as high temperature or biomedical, ceramics are a better choice because they do have better properties suited to those, such as they are chemically inert and they have a very high service temperature. They can withstand temperatures that silicon can't. An example is a high temperature electrostatic actuator, which can be used to detect lasers and change the voltage based on the input of the laser. Processing of the materials. Ceramic fabrication and MEMS are generally grouped into three categories. There's additive, which is what 3D printing uses, patterning, which is what is used in photolithography for silicon, and subtractive, although this is rarely used because it is very expensive. One of the methods for additive is vat polymerization, which you can see on the right. And another one is the ceramic extrusion method. This is used for gears, microtubes, and actuators. Specifically, types of materials, types of ceramics that are often used, one of which is silicon carbide, which is using a soft lithography, etching, or extrusion, as well as lead zirconate titanate, which is a piezoelectric material, like the inkjet printer I mentioned a few slides ago. And this is manufactured using lithography, deposition, or micromachining. The microstructures for the two ceramics I mentioned before are here. The first one is silicon carbide, which is a hexagonal structure. And the second one is lead zirconate titanate, which is a perovskite crystal structure. For the rest of the presentation, I'll be talking about specifically lead zirconate titanate. It is a metallic oxide with a perovskite crystal structure. Perovskite has the formula AbX3, where X is usually oxygen, and it can accept many different cations as the base crystal is neutral. Due to its highly crystallized structure, PZT can be used at extremely high temperatures before its Curie point is around 350. So it could be used at extremely high temperatures before it loses its magnetic properties and its piezoelectric capabilities. As I said, it is a piezoelectric material, which becomes polarized when under stress. So piezoelectric materials work by when a charge will flow from one side of the material to the other with the direction dictated by the type of stress. So if it receives compressive stress, it would give a flow from one end to the other. And if it was given tensile stress, it would flow the opposite direction. Inversely, if you pass an electric field through it, it will react and compress or stretch depending on the direction of the field. Finally, it is also a pyroelectric material, which means that it develops a voltage difference when exposed to a temperature change, which means it's a good candidate for measuring temperatures because it can use the voltage to understand how much the temperature has changed. Finally, materials processing microstructure property relationship. So nearly all processing methods for PZT, lead zirconate titanate, involve heat in order to bind the lead zirconium mixture and the titanate together. There are 4 different methods that I've listed here. There are others. One is the Sol gel method, which uses evaporation, sintering, which uses heat, extrusion, which is pushing it through the pump, through the hole, like I mentioned a few slides ago, and finally micro contact printing, which is the photolithography method that I mentioned earlier. Each of these different methods for processing PZT can change things such as the phase composition, the grain size, the homogeneity, and the microstructure. PZT is often doped with other elements. Acceptor dopants create anion vacancies, which leads to a hard PZT, which increases the piezoelectric effect, but decreases the structural rigidity, whereas donor dopants create cation vacancies, which leads to soft PZT, which has the opposite effect. I did want to talk about one thing I thought was very interesting, which is morphotropic phase boundary. So basically, by changing the composition of PZT, specifically the molecular ratio of zirconium and titanium, you can increase the permittivity at the morphotropic phase boundary. This means that you are increasing the piezoelectric effect. So in between the phase transition between the tetragonal and rhombohedral crystal phases of the PZT, that change in structure maximizes the electromechanical properties. It was found that a rhombohedral orientation near that morphotropic phase boundary greatly increases the piezoelectric abilities of the material, actually regardless of the material itself. So it actually has applications where you may be able to use a purer material besides PZT, and as long as it has that rhombohedral orientation near the MPB, the morphotropic phase boundary, you may get piezoelectric properties. And finally, there are all my references. And thank you for watching.